Hi, everyone. My name is Coey. I'm at the MIT Operations Research Center, and today I'll be talking about conic benchmarks and algorithms in Hypatia. And this is joint work with Leah Kapelovich and Juan Pablo Vielma. So this talk is based on our new paper that's on arXiv called Performance Enhancements for a Generic Conic Interior Point Algorithm. So Hypatia is an open source, highly extensible conic solver. It's written in Julia and accessible through either a native interface or JUMP. And Hypatia has various options for preprocessing, solving linear systems, interior point stepping, etc. Or you can plug in your own custom procedures. Hypatia implements a primal dual interior point method that's based on the theory of logarithmically homogeneous self-concordant barriers for proper cones. And a key design feature of Hypatia is our generic cone interface, which allows the user to define a proper cone and its dual cone by implementing a short list of oracles for either the cone or its dual cone, not necessarily both. So in a recent paper, we give computational arguments for expanding the class of cones that's recognized by conic solvers. So to do this, we describe 7 applied examples, and we show that compared to the few standard cones that are recognized by MOSEC9 or SCS, exotic cones, a much larger class, permit smaller, simpler, more natural formulations. And Hypatia can solve these natural formulations more efficiently than either Hypatia or MOSEC9 can solve the equivalent standard cone extended formulations for those examples. Okay, so for some algorithmic background, various non-symmetric methods have drawbacks, and these were fixed by the SY algorithm by Skaja and Yat in 2015. So this algorithm traces the central path of the homogeneous self-dual embedding down to a conic certificate if one exists. And it relies on an observation by Nesterov that good prediction directions can be obtained if the current iterate is near the central path. So this algorithm only needs a few tractable oracles for the primal cone. These are an initial interior point, a feasibility check, and gradient and Hessian evaluations for an LHSCB. So over the last few years, we have found that for many cones, these oracles can be implemented in an analytic way. So this means we don't need to implement expensive, numerically unstable, iterative procedures, such as optimization, which require tuning. Usually, however, we've found that analytic oracles are not known for the conjugate LHSCBs, or indeed for any dual LHSCB. So we improve SY, which is implemented by the MATLAB solver Alfonso, in 2 main ways. First, we generalize it to allow cones with either primal or dual oracles. And this is important because a lot of our example formulations have mixtures of cones with primal oracles and others with dual oracles. And secondly, we enhance the interior point stepping procedure of Skaja to improve the practical performance. Okay, so let K be a proper cone, meaning it's closed, convex, pointed, full dimensional. And we're going to say it's a subset of RQ, so it's a vector cone. And this is without loss of generality. Let F be an LHSCB for K. Now we call K and its dual cone K star exotic cones if we can implement the following oracles for K analytically. The initial interior point, a feasibility check, which just takes a point and tells us whether it's in the interior of the cone, gradient and Hessian evaluations. And these 4 oracles are those required by Skaja. But we add another one, a 5th one. This is the 3rd order directional derivative oracle, which we call the TOO, and it has this form. So we've noticed that requiring an analytic procedure for the TOO does not seem to be more restrictive than requiring analytic procedures for the gradient and Hessian. So it doesn't seem to matter in terms of how restrictive this oracle is. So we note that the TOO we have is simpler than higher order corrector terms that you may be familiar with. And we also use it somewhat differently. So Hypatia has 23 exotic cones already predefined through the generic cone interface, but this actually makes many more than 23 cones available to the user. So first of all, for example, all but 4 of these cones are non-symmetric. So the dual cones are all different. So that nearly doubles the number of cones that the user can use. Some of the cones also have both real and complex variants. And all these cones are parameterized by at least one dimension. Some are also parameterized by numerical data. And as I said, all the oracles we implement are sort of analytic, so no iterative numerical procedures that have to be tuned. Now, we note that Hypatia, beyond these 5 oracles, also allows optional additional oracles that can improve performance. For example, a dual cone feasibility check or inverse Hessian product oracles. And at every new point, Hypatia will always call the feasibility check first because the other oracles are only defined at strictly feasible points. Then it will call the gradient, then the Hessian and the TOO if they're used. And along the way, Hypatia caches data and factorizations for reuse, just to be as efficient as possible. On the next slide, we show oracle time complexity estimates for the cones we've implemented, ignoring constants. And this table shows that the TOO is never more expensive than the other oracles. And in the paper, you can see, the definitions for all of these parameters and these cones. Okay, so Hypatia's primal dual conic form looks like this, and it is the same as the form used by the CVX solver, which only recognizes symmetric cones. So the user specifies a primal form problem through Hypatia's model interface. And here C, B, and H are vectors, A and G are linear maps, and K is a Cartesian product of exotic cones. This model is parameterized by any Julia floating point type. So the algorithm will then be performed in that same floating point type. So you could get certificates in arbitrary precision using big float, say. These linear maps here, A and G, are typically sparse or dense Julia matrices. They don't have to be. K is specified as a vector of cone objects, which are defined through the cone's interface. And the dual cone K star there is simply a Cartesian product of the dual exotic cones. Okay, now we define the homogeneous self-dual embedding. So this is a self-dual conic feasibility problem in the primal dual variables and also in these scalar variables, tau and kappa. So we call omega an interior point if it is strictly conic feasible for that cone constraint there. And if omega is feasible for the HSDE, then S prime Z equals kappa times tau equals 0. And the list of exhaustive possible cases is if tau is positive, then we have an optimality certificate. We have a complementary solution from omega. If kappa is positive, then we have an infeasibility certificate either of the primal or of the dual. And finally, if tau equals kappa equals 0, then this particular omega gives no information about the primal dual statuses or objective values. And according to Skadja and Ye, if their algorithm finds a solution with tau equals kappa equals 0, then this holds for all solutions. And this means that the primal or the dual problem is ill-posed, or both. And Hypatia inherits this algorithmic property. Okay, so to assess the algorithmic enhancements that we will discuss next, we generate 379 conic instances in that primal form from 37 applied examples that are in the Hypatia repo. So all of these are primal dual feasible, except for some primal infeasible or dual infeasible ones. And for most of these examples, we actually implement multiple different formulations with different cones. And each predefined cone in that list of 23 is represented. So it's an extremely diverse set of conic instances. And of course, there's no sufficiently general conic storage format available to us. So we build all these instances on the fly using random seeds to ensure reproducibility. So here are some histograms summarizing those instances. On the left, we have the instance size, which is the affine dimensions, the sum of those. And on the right, we have the number of exotic cones in that Cartesian product cone. This table gives the names of the examples, the number of instances for that example, and a list of the cones that appear in at least one instance of the example. So that's page 1. And that's page 2. Okay, so now we're going to discuss the algorithm and our proposed stepping enhancements. So first, we define the central path of the homogeneous self-dual embedding. So to do that, we are going to set up some notation that's going to make it a lot easier. So first, we partition the cone indices 1 to k into the indices of cones with primal oracles and those with dual oracles. And we're going to concatenate onto the end of Z and S, the kappa and tau variables. Now we construct an initial interior point omega 0 by setting the cone points S and Z by calling the initial interior point oracle T sub k for each cone and the gradient oracle. We let E represent that 4x6 block matrix that was in the HSDE linear equalities. And we're going to assume that that's full row rank. And if it's not, then our pre-processing techniques, which we don't describe here, will handle that case. Now, the central path is an interior trajectory for the HSDE, parameterized by a positive mu. And it looks like this. And those first qualities are linear. The second set of equalities are nonlinear. And then we have a cone inclusion constraint. We define Lex-Gautier the complementarity gap function mu. And now, given these definitions, we can say that the central path starts at our initial point omega 0, which satisfies by construction mu equals 1. And as mu decreases down to 0, we approach an HSD solution from which we can obtain a conic certificate. So now we're going to define a function that gives us the proximity of a point omega to the central path for each cone k. And we call that pi sub k of omega. It turns out that if this is less than 1, then sk and zk belong to the cones. So this is via a Deikin ellipsoid proof. So that kind of ensures interiority, at least for index k. Now, we can think of some different options for aggregating these proximities, pi 1 to pi k. First, and this is what sy does, an L2 proximity. Another option, though, would be to use a maximum over these proximities, and this lower bounds the L2 proximity. Now, for this high-level algorithm, on the ith iteration, we have the current interior point omega sup I minus 1, and that is interior and close to the central path. And we're going to search for the next interior point, which also needs to be interior and close to the central path. And we can do this either via a prediction step, which decreases the complementarity gap mu, and thereby takes us towards an HSD solution. Or we can do a centering step, which decreases the proximity, taking us towards the central path. And over the course of these iterations, mu will decrease, and eventually we're going to terminate with an approximate certificate. So let's derive those directions. So first, let's drop the index k, just to keep notation simple. And we're going to differentiate that nonlinear equality condition. And the centering direction comes from analogy to a Newton step, and it keeps mu fairly constant. And the prediction direction, delta p, comes from treating the central path as a dynamical system and differentiating it with respect to mu. We take this a step further in our paper by differentiating again. And this allows us to derive third order adjustment directions, delta CT and delta PT, that adjust and actually depend on those unadjusted centering and prediction directions. So for a direction delta, it solves a linear system with a structured square LHS, which is fixed during each iteration of the interior point method, and a particular RHS vector. So here we give the form of the LHS, dropping that index k, and of the 4 right-hand sides corresponding to each of those directions. So you can see for centering that delta CT depends on delta C through the right-hand side through that TOO oracle. So you need to compute delta C before you compute delta CT. And similarly for the prediction. Because the LHS here is square and non-singular, each delta is unique. So now we're going to describe the basic stepping procedure that is proposed by SY and implemented by Alfonso Solver. So we fix some values of parameters, and we let J count the number of consecutive centering steps just before the current iteration. And this basic stepper looks like this. So on line 2, we choose whether to predict or center if we're very close to the central path, or if we've just taken more than 4 centering steps, then we do a prediction direction. Otherwise, we compute the centering direction. On line 9, we do a backtracking line search. So we find the maximum step distance in the direction delta that we can step while satisfying a proximity condition. And that proximity condition is a bit looser than the one on line 2. And then finally on line 10, we update the iterate. Now, the first step is always going to be a prediction step because recall omega 0 is exactly on the central path. Okay, so our first enhancement to this basic procedure. So the proximity conditions of the basic stepper may be too restrictive for ideal practical performance. So we're going to try loosening them. First, by using that maximum aggregate proximity, pi L infinity, instead of pi L2. Secondly, we're going to increase the beta parameter up to 0.99, which is just less than 1. So it's sufficient for interiority. So the prox stepper looks like this. On line 2, we loosen that proximity function. On line 9, we change the function again, and we also increase that bound beta. Our second enhancement incorporates the third order adjustments. So we modify that prox stepper that we just introduced by using an extra line search in the unadjusted directions. And we use that distance to rescale the TOA direction, scale it down, preventing over adjustment. So this is what it looks like. We compute delta U, which is the unadjusted direction, delta T, which is the TOA direction. And then on line 11, we do the line search in the unadjusted direction, delta U. On line 12, we form the final direction by adding delta U and a scale down of delta T. And then as usual, on line 13 and 14, we perform the line search in that final direction and update the iterate. Our third enhancement. So each of the 2 backtracking line searches that we did in the TOA procedure can be expensive because we have to do a bunch of proximity checks. So instead, we're going to try doing a single search that's on a curve that is quadratic in alpha and linear in the 2 directions. So this is what that looks like. On line 11, we define this curved trajectory. And then on line 12, we just perform a backtracking search along that curve. And the backtracking search looks very similar to the line search. It's just a different trajectory. Finally, we consider combining the prediction and centering phases like some other primal dual interior point methods. So to do this, we're going to have to actually compute all 4 directions. And there's some mathematical intuition on how we choose to do this, but I will skip that here. So here's what the combined stepping procedure looks like. So we do a curve search, again, that's quadratic in alpha and linear in the 4 directions. And then we update the iterate. Okay, so now let's look at some benchmark results for these 4 enhancements. So first of all, just to give some context, this is for the combined procedure, the last procedure with all the enhancements. So the instance size here is positively correlated with the solve time, as we'd expect. Here we show some histograms for iteration count and solve time of both the basic stepper, which is similar to Skagier and Alfonso with no enhancements, and the combined stepper, which incorporates all 4 of the enhancements. We can see that the solve times here span around 7 or 8 orders of magnitude. So it's a very, very diverse benchmark set in terms of the sizes and solve times of these problems. Okay. All 5 of the steppers from basic to combined solve a similar number of the 379 instances. And this is because we don't impose any time or iteration limits in our testing. If we had imposed limits, the enhancements would actually significantly improve the number we solve. For each of these instances, at least one of the stepper does converge. So in the paper, we show multiple different types of shifted geometric means just to give a complete unbiased picture of the results. And because the relative improvements we see over these measures agree quite closely, here in this presentation, we're only going to show one type of shifted geomean. and that is on the 353 instances on which every stepping procedure converged. And here's what that looks like. So we can see, for the 5 different steppers, how many each of them solved. We can see that the number of iterations and the solve time, those shifted geometric means improve by a reasonable amount for each one of the 4 enhancements. And overall, comparing basic with combined, so that gives us a sense for how well all 4 enhancements do together. The iterations and solve time improved by at least 80% and 70% respectively. In the paper, we also show subtimings for key algorithmic components, and we use these subtimings and how they change to understand the intuition of how these enhancements are actually affecting our performance. So one thing we note is that we tend to see larger improvements where improvements are really needed. So here we plot the relative improvement of iteration count and solve time against the iteration counts or solve times for the combined stepper. So we see that, when we tend to take more iterations, the relative improvement from basic to combined tends to be better. And similarly for solve time. The iteration counts of all instances improved by at least 33%. And for the solve times, there are some solve time regressions. However, those regressions are only on instances that solve fairly quickly. Okay, so some pairwise performance profiles. So recall that to read a performance profile, the vertical axis is like the proportion of instances, and the horizontal axis tells us that a particular solver was within this factor of the best in a log to base 2 scale on that proportion of instances. So on the left, we have the iteration counts for basic versus combined, and we see that they always improve. And we see that, typically the improvement is between a factor 4, 2 to the power 2, and a factor 8. On the right, for solve times, we almost always see improvements, and it seems sort of the median improvement is around factor 4. Now we break it down by enhancement. So up the top here, we have basic versus prox. So this is the first enhancement, loosening the conservative proximity bounds. So this influences the iteration count and the solve time in a very similar way. So this suggests that solve times improvements are driven pretty much entirely by the iteration count improvements. In the bottom, we see the effect of the second enhancement. So that is introducing the 3rd order adjustments. So on the bottom left, we see that the iteration count always improves. And interestingly, it improves very reliably. So the verticality of that graph speaks to how consistently the 3rd order adjustments improve our, the quality of our directions and therefore the number of iterations. On the right, we see that the effect on time is less consistent. In fact, the time does not always improve. So this makes sense because we now have to compute the TOO for every cone. We have to solve for an extra direction and perform an extra line search. Now we see the effect of the 3rd enhancement, the curve search. So this replaces the 2 line searches with a single search on a curve. We see that as expected, it improves the solve time because we're only doing 1 backtracking search. But it also unexpectedly improves the iteration count. So this was a nice side benefit. And this may be because it's a more dynamic approach. And finally, we see the effect of the 4th enhancement combining the prediction and centering directions. On the bottom left, it improves the iteration count quite significantly and fairly reliably. On the right, it has a less consistent effect on the solve time. However, we note that for larger, harder instances, it tends to help more. Here are some references. And thank you for listening.